Alright, so welcome to Spatial Analytics in R. So here we're going to be discussing how we can implement machine learning in R, specifically using the Caret package. Note that Caret isn't the only way to do machine learning, both in R or outside of R. However, I found it to be very powerful and intuitive and pretty robust. So that's what we're going to focus on here. Alright, so before we get into it, I just wanted to provide some examples of how we can use machine learning to actually make predictions over a map space. Alright, so one of the very common applications of machine learning in remote sensing is land cover classification. So trying to predict using images and training data what an area in the landscape is likely to be. So forest, water, grass, herbaceous, development, so on and so forth. Here's an example of a product that was produced using the random forest machine learning algorithm, in which we created a high-resolution land cover data set for Preston County in West Virginia. So this process incorporated geographic object-based image analysis, LiDAR data, ancillary data, and machine learning to try to make a land cover prediction. So that's one common application. Here's another application that's somewhat related. So this is trying to predict whether grass areas are the result of mining, so mine reclaimed grasslands, or just other grasslands. So this was done for a portion of southern West Virginia. So the idea here was kind of a binary classification. So try to predict whether an area that was grass was either mine-related or non-mine-related. And this again was done using random forest. This is another example where instead of trying to predict something that is categorical, we're trying to predict something that is continuous, or specifically probabilistic. So in the case of a probabilistic prediction, your goal isn't really so much to say this is one thing or another, is to say what the likelihood of it being a certain thing is. This is from a manuscript I worked on a few years ago, where we were trying to predict the likelihood of a location being a wetland just based on terrain characteristics. So in this map output, the orange areas, the darker orange areas, would indicate locations that were likely or more likely to be a palustrine emergent wetland, whereas darker green areas were areas that were predicted based on topography to likely to be a palustrine forested or palustrine scrub wetland. So here again, not trying to predict categories, but instead trying to predict something probabilistically, so the likelihood of something. We can also use machine learning to try to predict into the future. So here is a output from a machine learning prediction in which we were trying to predict the likelihood that an area would be mined, or specifically surface mined, in the future. So this blue grade extent here represents the Mid-Atlantic region. We made predictions not in the entire area because there's not coal seams everywhere, but for where there were coal seams, you try to make a prediction of how likely it was that that area would be mined in the future. So make predictions in the future. These are also, obviously there's lots of applications in which we would like to know how something might change or in the future. For example, predicting the weather or changes resulting to, say, climate change or changes to an ecosystem. Okay, so before we get into talking about the method of creating a prediction, let's talk about types of prediction. And here we're mainly going to focus on the types of variables that we are trying to measure or predict. Okay, so first off, you might be trying to predict something that is a continuous or numeric variable or outcome, so interval or ratio type data. Again, machine learning is not the only way to do this. There are other options, such as linear regression or multiple linear regression, if the assumptions are met to use those methods. You could also use polynomial regression, but here again we're mainly going to focus on machine learning-based processes, like support vector machines or random forest. Here's an example of an output that would be a continuous variable measured over a spatial extent. So this is a product from the National Land Cover Database, specifically from the 2011 product. So here, all the areas in green represent forest, and darker shades of green indicate a higher percentage of canopy cover. So effectively, this is a continuous or numeric estimation of percent canopy cover. So this was specifically done using the random forest algorithm. So again, a continuous variable, percentage. As some of our prior examples shown, you can also not predict something continuous, but something categorical. So things like types of soils, types of vegetation, types of ecosystems, types of land cover or land use. There are lots of methods for doing those types of predictions, such as logistic regression, maximum likelihood, parallel pipette, minimum distance to means. So some of the common parametric methods that are used in remote sensing image classification. But again, here we're going to mainly focus on machine learning classification methods. Just as a side note, what we're really interested in here specifically is what you would call supervised classification. So instead of trying to predict so we were basically trying to predict using examples or training data, as opposed to letting the computer basically cluster the data. So here's an example of a classification output. So this is a Sentinel-2 image for the area around Vancouver in British Columbia. So our goal is to go from the image as predictor variables and use examples of the land cover as training data to create a land cover classification from it. So again, this would be an example of supervised classification because we're giving the computer training data and it uses that training data to try to make a prediction. Another option is unsupervised classification or clustering, in which the computer tries to cluster the data into unique clusters based on the characteristics, and then later on the user will assign clusters to useful categories, so like land cover categories. So again, these type of processes can be done with machine learning, but what we're mainly going to focus on here is supervised classification, where we actually provide the computer training samples or examples. If you're interested specifically in how we can apply machine learning for image classification, I would suggest looking at this paper. This is a review article by myself, Dr. Tim Warner, and Fong Fong. Here we looked at basically an applied application of machine learning algorithms for remote sensing image classification. So if you're interested in kind of the applied nature of this, I would recommend that paper. Note that this is an open access, so if you want to read it, you can get it through open access. You don't have to pay for it. Some of the findings in this paper I'll mention throughout this talk. Okay, and then another type of prediction you may want to make would be a probabilistic prediction. So the likelihood of something as opposed to a hard classification or categorizing a map. So these were some examples we've already looked at. So predicting the likelihood of an area being a wetland, predicting the likelihood that a area will be mined in the future. So again, the goal here is to not get hard categories, but the likelihood of something. That can be done with methods such as logistic regression, maximum entropy or maxent modeling, and also some machine learning methods like random forest. Again, here we're mainly going to focus on the machine learning methods. And then lastly, it's also possible to predict count data, so the number of or count of something. So, for example, the number of incidents of a disease in an area. Traditionally, this has been done with Poisson regression, but there are some machine learning methods that can also predict to count data. Note that that's not something we're really going to look at here, but I wanted to mention that because it is something people commonly want to do. Okay, so now we're going to look at the process. So how do you actually make one of these predictions? Here we're not going to focus specifically on any algorithm. We're just going to talk in general about how this process is undertaken with some specific caveats. All right, so this flow diagram outlines how you would go through the process of creating a prediction. So again, here we're focused on supervised learning, where you give the computer examples of what you're looking for and allow it to try to use those examples to try to make a model which can be used to make predictions. So in this context, you're going to need training samples. And since we're specifically looking at making predictions over a map space, these training samples generally have to be spatially explicit. So they actually occur on the map. You know where they are. So once you have training samples, you also need to have predictor variables. So these are things that you think might be useful to try to predict the thing you're trying to predict. So things like temperature or precipitation or image bands or terrain information or distances from input ancillary geographic features. So again, spatially explicit because our ultimate goal is to make a map in this case. Once you have training data and predictor variables, then you're going to use some classification methods to try to make a prediction or model. Again, there's lots of different algorithms, and we're going to look at a handful of the more commonly used ones here. Once you have a model, you can then use that model to predict to unknowns, so predict new samples. This prediction could be made to the entire population. So for example, every pixel in a data set, like a raster grid, every polygon in a vector feature class. So again, if you could predict everything, then you could maybe make a wall-to-wall map or predictive surface. It's also very important to try to validate your model to assess how accurate it is, how good of a job it's doing. So we generally do that by comparing the model to randomized validation samples. So using our population and our validation samples, we can validate the model and make a spatial map output. All right, so just kind of to summarize that, first, with the process, you're generally developing training data. You also need to develop predictor variables. So you need both of these inputs before you can create a model. To assess your model, you're also going to need to develop validation data. Once you have your data, you can prepare it and then read it into R. Again, you could work in another environment, but here we're mainly focused on machine learning within R. You may have to do some pre-processing or optimization of the algorithm. Again, we'll talk about that later. Then you need to, once it's prepared and ready, you need to run the model. Once you run the model and it's created, you can use it to predict your validation data and then validate the model. Again, later on, we'll talk about some of the common accuracy assessment methods that are used to validate maps. Then, if your model is good enough, you can use it to predict the entire spatial extent. So predict, say, every pixel in a raster grid or every polygon in a layer. And you can save that result out to use in a different environment. So in your GIS software, maybe to make a web map out of or include in a report or do additional statistical analysis. So let's look at some of these key steps in a little bit more detail. So again, the training data is super important. In my opinion, the quality of the training data is the most important part of getting a good quality map output. You know, it's garbage in, garbage out. So if you give the computer, the algorithm, bad examples, it's not going to do a very good job at making a prediction. So in terms of map production and spatial modeling, there are a few key criteria of training data. First off, they need to be spatially explicit. So you need to know where they are in the map space and the projection. They need to be representative of the population. So for example, if you were trying to predict the habitat for a specific tree, and that tree grew in, say, bottomland riparian areas, and it also grew on certain side slopes, but you only gave the algorithm examples on the side slopes, then it wouldn't know anything about the characteristics of how it would grow in the riparian areas. So again, it needs to really represent the full population. So it needs to see the variability. You need to have an adequate number of samples. What that means is not always easy to fully define because there's a lot of factors that could impact that. So, for example, how complex the signature is, what algorithm is being used, My general rule of thumb is I try to collect the most training data that I can given the limitations. So limitations in terms of time and man hours, available data, funding, ability to do field work. So again, this is generally limited because we live in the real world. Even though we live in the world of big data, we don't always have enough quality data to, say, train a model. So the goal is just to get the best you can, get the best data you can with the limitations that you have. You also, instead of just having an adequate number of samples in general, you also need to have an adequate number of samples per category. So it's very common for a landscape to not be evenly proportioned among, say, categories of interest. So, for example, wetlands or water might only be a small proportion of the area. This is also seen in areas outside of GIS and remote sensing and spatial science. One good example is fraud detection with credit cards. The vast majority of credit card transactions are likely to be not fraudulent, so to be legitimate transactions. So it might not be difficult to get enough examples of fraudulent transactions to train the model. So again, it's not just number of samples, it's a good representation of each, say, category, or if it's binary, like true and false, yes and no. And then this probably doesn't need said, but obviously it needs to be accurate. So if the quality of the training data is, again, very important. So if you give it training data that's very noisy, or there's features that are mislabeled or measured incorrectly, or say georeferenced incorrectly, then that could be a big issue. So again, garbage in, garbage out. A note on pseudo-absence data. So it's common for us to map where things are as opposed to where things aren't. So for example, if you were interested in creating like a habitat model, you might be able to easily find examples of where a certain thing occurs, so a tree or an organism of some kind, but you might have a harder time finding examples of where it's not. Again, that's commonly just not mapped. However, a lot of algorithms require examples of both presence and absence, so like true and false. So if you're in a situation where you want to use an algorithm, but you only have presence data, you're going to have to find a way to develop absence data. That can be done by creating what we call pseudo-absence data. So this could be basically random locations that are unlikely to be true points or presence points. I've had to implement this for some of my own work with wetlands. So we have examples of wetlands, but we don't necessarily have examples of not wetlands. So how do we get examples of not wetlands? Well, we basically would create a randomized random validations absence samples that occurs in areas that aren't wetlands. And are not within wetland extents, and are thus likely to not be wetlands since they are not very common on the landscape. So that's the concept of pseudo-absence data. Again, some situations that might be hard to do because there could be a good chance of an unmapped location being the thing that you want it not to be. So it wouldn't really be absence. And then if you have issues where you really can't create absence data, then you can try to implement methods that can just use presence data only. One example of that is maximum entropy or maxent, which is available through a Java interface, and also you can use it within R. We're not really going to look at that here, but I just wanted to mention that that's a possibility if you want to do presence only modeling. You don't have absence data. Okay, so you also need predictor variables. So again, these are features or variables that may be predictive of the thing you're trying to map or estimate. So again, since our goal here is to make an actual map output, these things need to be spatially explicit. So you need to know where they are. They also need to be accurately georeferenced so that positional errors don't factor into the to the analysis. They should be accurate and precise. So again, garbage in, garbage out. Timeliness might matter. Depends on what you're trying to map and what specific variables you're looking at including. So for example, timeliness of something like bedrock geology might not be an issue because bedrock geology changes at geologic timescales as opposed to like human timescales. In contrast, something like census data or extent of development might be more of an issue because it can change and update over time. So whatever variables you use, you should think about whether or not they are adequate enough in terms of their temporal resolution or timeliness, or whether or not they're updated for the modeling that you're doing. Other than just like temporal resolution, we also worry about spatial resolution. So if you're trying to produce an output that is a 30-meter grid, it may not be adequate to include, say, a 1 kilometer, like temperature surface as a predictor variable, because it's just simply too coarse spatially. Sometimes it can be difficult to find data that's of adequate quality and resolution and up to date for your modeling. This can be very challenging. My last point here is that it needs to be available, which seems like an odd thing to say, but when you think about it, we sometimes might assume that some data set exists and is of adequate quality for our needs, when in fact it's just not available. If that's the case, your options would be to not include it, or you could try to actually produce that data set if you have the funds and times to do so, but in many situations it's not going to be possible. So again, we're generally going to have to make our estimations, our predictions with a limited set of variables. We can't have everything that we want. But again, you should think about the quality of the data that you do have. I want to make a note on how we get raster data into R, because a lot of the predictor variables that we're going to use are going to be raster grids. So raster data can be read into R using the raster package. So this package is designed specifically to read in geospatial raster data. One thing that's nice about raster data is that it's actually a fairly simple data structure. It's effectively, if it's a single band, it's a matrix, which R can read and use fairly readily, or if it's a multi-band, it's effectively just an array. So this data is pretty easy to use and work with. Note that if you read data in with the raster package, everything's working correctly, and that there's no issues with the layer. R should automatically understand the cell size, the spatial extent, and the projection information, and also like the number of bands. There are a couple different ways to get raster data into R. If you're reading in a single raster layer, that can be accomplished using the raster function. So that can read in a layer from a URL or from local disks, like an image file or a TIFF file or something. If you want to read in multi-band data, that can generally be done using a raster brick or a raster stack. So we basically have three types of raster objects in R that are created using the raster package. So a raster layer, again, is a single band layer, whereas a raster brick is multi-band and a raster stack is a multi-band. What is the difference between a raster brick and a raster stack? So a raster brick has to reference one multi-layer or multi-band file, or it has to itself be a multi-layer object that is loaded from memory. So it has to basically reference the same file. So for example, you could use a raster brick to read in a Landsat image where all the bands have already been stacked into a single image. In contrast to that, a raster stack doesn't necessarily have to reference the same file. So you can have a stack that's produced from multiple layers or multiple files on disks. So they virtually connect several raster objects written to different files or in memory. You could also have a raster stack read in all the just from a single layer, but the point is it doesn't have to. Generally speaking, processing will generally be more faster and more efficient if you use a raster brick. So that can be important, especially if you're using large data sets. But raster stacks have the advantage of allowing for pixel-based calculations on separate raster layers. So again, you don't have to have all your input from the same layer. So in short, if you're going to read in multi-band data, you're going to use a brick or a stack. As a final note about raster data in R, generally speaking, R is going to be less forgiving than other spatial analysis tools such as ArcGIS in terms of differences in origin, projection, spatial extent. Generally speaking, I found that it's best to just make sure that all of my data layers have the same origin, same spatial extent, same cell size, same number of cells, so there's no issues with overlay. One way that I do that is just simply to read all the data in as a raster stack as an individual file. Just as some side notes, there are ways to do some pre-processing in R outside of R. I personally find that I like doing my data prep in my GIS software like ArcGIS. So just as a few kind of side notes on techniques that you might use to try to prep your data. So you may want to extract out a subset of your raster data. That can be done with extraction methods, for example, in ArcGIS, such as extract by mask or extract by point or extract by circle, polygon, rectangle, whatever. One that I really like is extract by mask. That allows you to basically extract out all the cells that fall within a mask, like a polygon or a raster mask. Kind of the opposite process would be trying to not extract out a portion of a raster, but combine multiple raster grids into a single grid. So that can be accomplished using the Mosaic to new raster tool in ArcGIS. So, for example, if you had 5 or 6 digital elevation models that you want to merge into a single model, then you could do that using Mosaic to new raster. When you do this, you have to specify the pixel type, 8-bit, 32-bit, float, 16-bit, whatever, the spatial reference, the number of bands, the cell size, how overlapping will be dealt with in terms of coming up with a new pixel value. Again, one concern with this would be that you might be able to produce a single grid from these multiple inputs, but that grid might be very large and might be difficult to read into memory and to use and to predict on top of. So you may find that you might have to actually perform your predictions out on tiles or subsets. Okay, and then another thing you might want to do is stack grids. So here the idea is to take single bands and merge those into a single file. That can be accomplished in ArcGIS using the composite bands tool. So you can give it a stack of bands and then it will create a single composite multi-layer file out of that. This can also be accomplished using the stacking tool within ERDAS Imagine. Note that this is commonly done with image data, so like red, green, and blue bands are combined to make an RGB composite image. However, you can do this type of stacking not just on imagery, but on really any type of raster data. So for example, if you produced a set of terrain derivatives, you could stack those terrain derivatives into a single band raster. Okay, so as I mentioned before, I generally like that as a pre-processing step. So to deal with issues of projection, extent, origin, cell size, number of cells, number of rows and columns, I like to just take all my data and stack it into a single grid and then read that entire grid in as a raster brick or raster stack and then predict on top of that. That's not the only way you can do it. That's just one way that I have found is very forgiving and you don't have to worry about alignment issues. Okay, you also are going to need to have some validation data. So again, it's important to assess the quality of your output. And later on, we'll talk about some of the methods that we use to assess that. Again, you can basically make a model of anything, but that doesn't necessarily mean that that model will be useful or at all accurate. So it might be complete and utter nonsense. So in order to actually assess that, you need to actually try to quantify the error rates. So with validation data, it's very important that the data are unbiased and randomized. If you hand select samples to compare your result to, that could be biased. So generally, we deal with this or make sure that our data are unbiased by by making sure that it's random. So we could set up things like random points or select random polygons from a set of polygons or random features from a set of features. Generally, it's a good idea if your validation data do not overlap with your training samples. Most machine learning algorithms are going to do a better job at predicting samples they've already seen than new samples. So if some of your training data are also included as validation data, that could artificially inflate the quality of the output. Another issue is correctly proportioned. This is very important in the context of maps specifically. So, for example, if you're mapping land cover and only 10% of your area is wetland or water or something, then your validation data should be roughly that same proportion. So to actually assess map accuracy, we're generally interested in assessing it at the correct proportions, as opposed to, say, a balanced sample where you have an equal number of validation samples in each category. Note that we don't always do that, especially in remote sensing and GIS. So you may see a lot of studies where the validation isn't done on a correctly proportioned sample. And obviously, this probably goes without saying, but your data need to be accurate. So if you create some validation data and it's very flawed, you could be comparing your model to something that's actually not much more accurate than that. So the assumption here is that your validation data are much more accurate than the model. So you're comparing to something of higher quality. We try in remote sensing and GIS and spatial science to not use the term ground samples or ground truth, because ground truth implies that your validation data are 100% correct, but no data are 100% correct. The goal here is to have data that's just better than the model to compare it to. So again, just a couple kind of practical points. I like to prepare my training and validation data outside of R using my GIS software, like ArcGIS. So random sampling, digitizing, so on and so forth. There are lots of summarization methods available to summarize data on polygons or points or whatnot. If you want to not read your validation and training data in spatial layers, like as a feature class or a shapefile as raster data, you can take the attribute tables from your spatial data and convert that into a CSV file and read it in as a CSV using read.csv in R. Just to mention a couple tools that you might find useful for prepping your data. One tool is Zonal Statistics' table. So this allows you to collect statistical measures from a raster grid within a zone or feature. So for example, if you had small polygons that represented, say, watersheds, you could calculate elevation statistics and store that in a table. So again, zonal statistics is generally used to calculate or obtain summary statistics for continuous data, like an elevation surface or a slope surface, relative to some feature or boundary, like a polygon or raster boundaries or masks. If you're specifically interested in summarizing categorical data, like land cover or soil types or vegetation types, that can generally be done using tabulated area. So tabulated area is used to summarize categorical raster data relative to boundaries, whereas zonal statistics is used to summarize continuous raster data relative to boundaries. You can also summarize data relative to points. Within ArcGIS, there's a tool called Extract Multi-Values to Points and a tool called Extract Values to Points. These tools allow you to extract raster values at point locations. Note that this can also be done in R using the extract methods with your spatial data. I just prefer to do this outside of R in my GIS. So, for example, if you wanted all the elevation, slope, land cover, other raster measurements at a point, you could use these tools to extract those values and put them in the attribute table. So, storing your predictor variables along with your training data. Okay, so the next section we're going to look specifically at how machine learning is implemented in Caret. Again, there are multiple ways to do machine learning, both in R and outside of R. Here we're focusing on Caret because I found it to be very useful and it's very standardized. So you can run a variety of different algorithms using effectively the same syntax. Okay, so why use Caret? Again, I've kind of pointed some of these out, but there are some other options or some other points to make. So first off, it allows you to implement a variety of machine learning methods using the same syntax. So you don't have to learn how to use a bunch of different packages to do a bunch of different machine learning, to utilize a bunch of different machine learning algorithms. You can just do it all in a similar interface. It has built-in methods for you to optimize the user-defined parameters for the algorithm, which can have a pretty big impact on the quality of the output. So it's important to be able to do that and do it fairly easily and efficiently. It also allows you to do some pre-processing on your data, such as calculating principal components or scaling and centering the data. It also allows you to validate the model. So it can build accuracy assessment like error matrices, calculate root mean square error. Again, it's fairly robust. There's many different methods that you can implement. It's very standardized. So again, you run a multitude of different algorithms using very similar syntax. It's fairly reproducible. You can set random seeds, for example, to get the same results. So in short, it's a very powerful package. Again, Caret stands for Classification and Regression Training. It was developed by these people you can see here in the documentation. Just like with any R package, it has its own documentation. So if you click on this link here, that will take you to this R documentation specific to Caret. There are many different methods available. Here is a link to a website that lists many of those methods. We're going to focus here on some of the more common methods that are used in GIS and remote sensing. So we will use KNN or K nearest neighbors using the KNN method. We'll use RPART to produce decision trees. We'll use C5 to produce boosted decision trees. We'll use Ranger or RF to produce random forest, and we'll use SVM radial for support vector machines. Again, if you have an interest in using an algorithm that we're not specifically investigating here, there's a good chance that that algorithm has been implemented into Caret, unless it's maybe like a deep learning method or something. So I would recommend going to this page and seeing how you could implement that specific algorithm. And as a side note, before we move on, I just wanted to say that, again, this is not the only place that you can use or implement machine learning. So there are other tools such as MATLAB. You can use individual packages in R. Two common tools that people use to do machine learning outside of R is Weka, which is free, and also within the Python programming language, you can use scikit-learn. Again, we're not really using those here, but I wanted to mention those as options, especially if you have experience with, say, Python. Okay, so here's what the basic syntax looks like in Caret for producing a machine learning classification. I have two different examples here with slightly different syntax. So if you're familiar with R, basically we're creating an object. This will be a model object. This is a function, train. It trains a model. And then these are the parameters that go into the model. So let's pull this apart. So here we're predicting a field from a table called train. And that field is class. So we're predicting class using all other columns in the table train. So this syntax with the curly and then the period basically means all other columns. So we're predicting class, so this is like Y, and then all the other columns will be our predictor variables, our X variables. All of those features are coming from the train object. So this could be a data frame, for example. In this case, it was a data frame. The method is the algorithm that we're using. So in this case, we're using RPART, or a single decision tree. Then we have some other options here. This preprocess argument tells Caret what pre-processing routines we want to potentially use. Here we're centering and scaling the data. So the data will be centered and scaled prior to it being used in the algorithm. Note that that's required or useful for some algorithms. It's not that big of a deal for others. And then we have this TR control set equal to this object train control. This is an object that contains some training control settings, which we'll talk about later. So things like how we will perform algorithm optimization. The second example here is pretty similar, but we're defining our y and x a little bit differently. This is the syntax I prefer to use. I think it's a little bit more robust. However, this syntax works also. So note up here we gave it a column that we want to predict and a set of columns that we're going to use to predict it, in this case all of them, and those columns are coming from a table. Here we're specifying the columns a little bit differently. So we're setting our y equal to the first column of this within this object train, and all of our x variables, our predictor variables, will be the second column through all of the columns in that data frame. So we're predicting the first column using all the other columns. So this is effectively the same thing. It's just a different way to input it. It's a different syntax. A couple of things about R. This is how you generally pull a column from a, say, data frame or matrix. So comma before indicates that it's a column. The comma after would indicate that you're pulling a row. So here we're pulling the first column, and this is 2 through, again, all the columns in the data set. This in-column function is just returns the number of columns. So it's 2 through the number of columns, so basically it's 2 through the last column. But note here, everything else is the same. This syntax, again, this is, again, one of the benefits of Caret, is this syntax is actually very similar for all the methods. So we could, for example, just replace this R part with a different method and just run a different machine learning algorithm. So again, that's one of the great benefits of Caret. Once you actually make a prediction, there are functions to actually, make a model, there are functions that actually use that prediction in some way, shape, or form. So here's a couple methods for creating a prediction. If you want to predict back to a table, you can use the predict function. So this is pretty simple. You basically call the model you created using the train function, and then you give it some new data to predict to. So this is generally going to be a table. Note that it's going to look for the same predictor variables. You don't need to have y. You don't need to have what you're trying to predict, but you do need to have the predictor variables, the x's. So generally, it's going to look for the same column names. They don't necessarily have to be in the same order, but they should have the same name. So if you call in data and your things you want to predict are named differently from the inputs in the training, then you're going to need to standardize them or rename it. So in short, this is the model that was created earlier. This is the new data that you want to predict. And then what it's going to do is spit out a prediction for each of those samples. So if it's continuous, it'll spit out a numeric prediction. If it's categorical, it'll spit out a category. If it's probabilistic, it'll spit out a probability, so on and so forth. Since in this course we're very interested in trying to predict not just to tables, but to spatial data, then there's also methods for predicting not to a table, but to something spatial. So here's an example of how you would predict out to a raster object. So the first input here is the raster object. So that's red. It's a stack of predictor variables as a raster. It's a raster stack or raster brick. Again, your band or layer names are going to have to match your predictor variables in order for it to work. And then you call a model, so the output from Caret. This progress window will create a progress window that shows how it's progressing. That can be useful because if you have a very large raster, it could take some time, so it's nice to know how well if it's actually moving along at a decent rate. Override is equal to true means that if you already wrote a raster output, then it's going to let you override it. If it's false, you're going to have to change the name of the output. It's not going to let you overwrite an existing file. And then lastly, we have here the file name. So this is the file name that will be written out to disk, so prediction.img. Note that I've had my best luck with TIFF files and image files in terms of output from R, and also reading into R. So in short, I would prefer using one of those methods over something like ArcGIS Grid. Okay, and then note that this file is going to get saved to your working directory. So if you wanted to save some place that's not your working directory, then you'd have to specify the entire file path there. So in short, as long as everything is standardized, so you have the same layer names or same column names, it's actually pretty easy to predict out to a spatial object like a raster or to an aspatial object like a table. If you want to predict out to a, say, shapefile or feature class, then I would suggest reading in your shapefile using the SF package, and then that will create effectively a data frame in which the geometry is stored in a list field, and then you can predict on top of that and then write it back out as a feature class or a shapefile. If you want to write out your result to a table, so instead of just storing it in R as a table or like data frame type object, you can write out to some table formats like CSV files or database files. One package that I've found to be very useful for this is the foreign package. So it has a function called write.dbf, which is write.database file, so it writes a database file. So this allows you to write your table out to a database file. I find this to be very useful because database files can open a lot of things. So for example, you could bring your database file back into something like ArcGIS as a tabulated data, and if it has a common field, you could join it back to a spatial layer to show your results spatially. Again, the output will be written to the working directory unless you specify another directory. Okay, so I think this is a good place to stop with the first lecture. We're about a third of the way through this. So what we'll pick up on next time is machine learning algorithms. So we'll actually talk about how conceptually some of these methods work that we're going to implement here inside of R for making our predictions. So I will see you in the second part if you want to continue. Thank you.